So good day once again. So our topic for today is about asterisk search algorithm in artificial intelligence. Intelligence is the strength of the human species. We have used it to improve our lives. Then we create the concept of artificial intelligence to amplify human intelligence and to develop and flourish civilizations like never before. The asterisk search algorithm is one such algorithm that has been developed to help us. We will learn more about what asterisk algorithm in artificial intelligence means, what are the steps involved in asterisk search algorithm in artificial intelligence and in implementation in other different programming languages. AI helps us solve problems of various complexities. Computational problems like path search problems can be solved using AI. Search problems where you need to find a path from one point to another, say point A to point B. Sometimes you need to solve it by mapping those problems to graphs, where all the possible outcomes are represented by the nodes. ASTRES algorithm comes up with the answer to this problem, created as part of the Shaky project aimed to build a mobile robot that has artificial intelligence to plan its actions. ASTRES was initially designed as a general graph traversal algorithm. It is widely used in solving path-finding problems in video games. Because of its flexibility and versatility, it can be used in a wide range of contexts, and asterisk algorithm is formulated with weighted graphs, which means it can find the best path involving the smallest cost in terms of distance and time. This makes asterisk algorithm in artificial intelligence an informed search algorithm for best first search. The most important advantage of asterisk search algorithm which separate it from other traversal technique is that it has a brain. This makes asterisk very smart and pushes it much ahead of other conventional algorithms.
So the condition is that the heuristics never overestimates the value. So basically, if you look at the straight line distance that we have, then you can never find a path that is shorter than this one. So basically, this straight line distance is always the shortest way, the shortest estimate of the distance between 2 points. So we know that it can never overestimate, yeah, because whatever true way we take will be longer. And that is this property of admissibility. Whenever I have this, and that is, I think, a very good way to remember this, that this shortest line distance is admissible, whereas others are not. So basically, the admissible heuristics are optimistic in a way that the true value that you have is bigger, and that it is in this example, it is the straight line distance as a very good example, which is by definition always the shortest way between these two paths. So let's now see how, in this remaining example, the A algorithm works if we use the straight line distance as our heuristics, and because we know that this is the straight line distance is an admissible heuristics, we also know that this A algorithm that we calculate here is also an A star algorithm. And later we look at an example where this is not the case. So A star applied here to this problem. We start again with Arad, that's the initial state, and we know the the distance that we have already traveled to get to Arad. And as this is an initial state, it's 0 because we haven't traveled yet at all. Yeah. So the F value for Arad is simply 0 for the travel distance plus the estimated distance to the goal. via the straight line distance, and that is just the 366 itself. So now let's look at the possible successes, and let's calculate the values. So, so if we go to CBU, it takes us 140 kilometers to get there. And then the estimate H is 253. Yeah. So basically here is it's written out. The F value for CBU is the G value for, so the distance we have traveled between Arad and CBU plus the H value of CBU, and that gives us a total of 393. That's simply the way you calculate it by the distance between the two places, and that gives you the estimation. So this CF between Arad and CBU is the G value of your state. And you calculate the same for Timisoara, just simply the travel distance between the two, plus the estimate, how far are you still away from Bucharest. Yeah, so here's the example. So these are the three successor states. And if we go to Timisoara, then we have to take 118. That's the travel distance. And then we have to look up the value 329 from our straight line distance from the H table. So these are the H values, and these are the G values. And then together, this gives me this value, Timisoara, here. So then basically, we have now for CBU a value of 393, for Timisoara 447, and for Zhirin 449. Okay, and then we apply our best first search algorithm by just choosing the best one, and that is CBU. So that is as it was before, but now the next step, things will change. So we expand the children for CBU, and these are then these four cities, and see that we can also go back. We can go back to Arad, but now the path between Arad starting point and Arad going back is one way and back, so it's 140 plus 140 is 280. And then it's the estimated distance between Arad and Bucharest again, which was 266. So this one gives us a very high value, 646. Făgăraș is the path that we had to travel from CBU to Făgăraș is 239, plus the path, the beeline distance to Bucharest, and that's 415 and so forth. And what you now realize is that you get for all these four successes of CBU, you get values that are relatively high. So we have now here 413 for this one, 671 for this one. And there are still the ones in our fringe from the previous level of search, namely Timisoara and Zhirin. And both of them have lower values than those for, no, sorry, we still have Făgăraș, which is in the list. But the important thing is that you also need to keep those in your ordered list. So the next step, oh, this one is also smaller. Sorry, this is the smallest of this one is the smallest, then we have this one, and then we have these two. So if you now expand, what is it, Râmnicu Vâlcea, then you get to the three children of it, and the way back, of course, to CBU. The left-hand one gets a certain value, 527, 517, 553. And that is now, again, it's always combined, the G value of how long, the path that I've already traveled, and the H value, how far away am I from Bucharest. And that basically then gives me orders on the different nodes. So this one is 417, but this one is 450. Yeah. So now the next one we have to expand is Făgăraș as the smallest one. You always have the global ordering in all the nodes, but they are now ordered according to both the distance from the goal and the distance to the goal, from the starting point and the distance to the goal. And then we have those two successors. They have values 450 and 591. And then basically you go back in your search to the highest value, which is now this one, Vitesse, and that gets you to Bucharest. And this is now the optimal solution. It's not the solution that we've seen before, because it now takes this detour and doesn't go this direct way to a suboptimal solution. And it finds this optimal solution only if the heuristic value is admissible, so never overestimating the real distance. So all you have to do in these exercises, when you are supposed to apply an A-star algorithm, is to calculate for each of the nodes in your search tree the value g, which is the complete distance back to the starting point, and the sum with the heuristics to the goal, the heuristic value to the goal. And then always just take the best one, so it's best search, but not greedy, not always the closest one, but the one that is combined with the past and the future, the best one. Yeah? Sorry, I don't understand the question. So whenever you find a goal state, you found the shortest path. No, you can also prove up front that you have an admissible heuristics. And in this case, I know that you can never travel here shorter than the estimate that we have with the B-line. Yeah? So, and as we can show that there is no better way rather than the heuristics predicts, so then you're done. Yeah? So then the properties of the algorithm that we've seen before is it's complete. It is exponential with the path length. And all the nodes have to be stored. So again, this is bad news, but as we've also shown, we don't need to expand the tree as much because we only take always the best ones in memory. And A-star gives you optimal solutions. And as your question says, you can prove upfront whether your algorithm will give you an optimal solution or not. And that depends on the definition of your heuristics. So something that confused me in the beginning a lot is that all the examples, or most of the examples that are broad, are on physical distance, physically traveling from A to B. And so this is another example in which I will want to work on in a minute. And that is you want to move this green box to the yellow box, or you want to move yourself, and you can only walk like this. You can't walk diagonally, so you have to either move to the right or to the left. Now the question is, you can't walk through this wall. What is the shortest path? And we are going to show how this works now in with all the different algorithms that we've seen. Yeah, so that's what I want to do the next 10 minutes. But it's not necessarily a distance, a physical distance that you want to calculate between this place and this place that you have in H. Or we could also use in our puzzle, for example, a heuristics that could be the number of the moves. So you want to do this as fast, as quickly as possible. So if in your exploration you count the number of moves, and for every move your G gets one higher, then you can combine that with the number of missed places, and that might give you an A algorithm that is quite effective. The problem here is that if I use this combination, so if HN is the number of misplaced tiles, then this heuristic is not admissible, because there is in principle no relation between the true distance and the number of misplaced tiles. So there could be an example where I have loads of misplaced tiles, but that still the number of moves is smaller. So that the heuristics overestimates the number of moves that I would have to take. But that would be something that we would have to prove analytically, whether this is admissible or not. But you can't. I don't think we can do this now. So it's. I'd rather claim that it's not admissible. So for this example, I just wanted to show you that you can apply an A algorithm here, even though it is not about physical distances. But for the example that I want to spend the rest of this lecture on, I want to use the physical distance. I don't want to use B-line distance, but Manhattan distance. But what I really would like to do now is to see whether you really understood all these different kind of searches. And I think we have 10 minutes left or so. Let's see. Yeah, so we have about 10 minutes left. So the task is, you are in this little corner, and you want to go to this corner up there. And how would breadth first search algorithm work to find the path that you have to take? And I suggest that we start, so we take a representation of this yeah. So then we can build a tree with these abbreviations, with these states. So how would you do that? So this is an exam question. So this is your task. Show us that you can do solve this problem with all these different methods. Yeah, you start with an initial state, I would suggest, and then do the moves. So the initial state is we are in 1A. And then you have possible moves. Yeah, 2A and 1B. Okay. So in those, if we now do breadth first search, we have put this one first in the fringe, and then we have put these in the fringe. Yeah. And then we don't have an ordering on the nodes. Yeah. So let's say we do this one. We still have this one in the fringe, but we have to explore the next states from 2A, and that is only 2B, I think. Yeah. And it is a queue, so we put it at the end. So we have to evaluate this one next. 1B is here, so we can go back, we can go there, and we can go up. So 2B, 1A, and 3A. Yeah?
That's 1C instead of
2A can also go back to 1A. Yeah, right. Yeah, and in this way we now this one is now first of the fringe. So we take all the steps that we can take from here. Yeah, and we explore the tree in this way. That's what we did last week. So that is pretty clear, I hope, and which it also did in the exercises. So now if you do the same with a depth first algorithm, you start with 1A. You have again this choice of 2A and 1B, but now we have them in the stack. So we take this one and then we evaluate 1A here and so forth. Okay, how did depth first iterative deepening work? We start with the starting point at 1A. Yeah, we search for a solution. We don't find one, so we throw everything away. Then we start again with the solution and go to the two places I can go, namely 1B and 2A. Yeah, there is no solution among them, so we throw everything away. And we do the same, 1A, 2A, 1B, and then we go depth first to this one. 2A was 1A again, 2B. Because this was not a solution, we now do depth first search. Remember, we do depth first search. This was not a solution, so we have to do backtracking. This is not a solution, so we have to do backtracking, and then we do this one and so forth. And once we've done that, we throw it again. Everything out, and we start again, and now we do it until level 3. And I think by now, I hope you have gotten the message. Yeah? So, now we have to think of some heuristics. And I suggest we use the Manhattan distance. Yeah? So what is that Manhattan distance between this one, x and y? Yeah? Yes? 1, 2, I'm sorry, 3. Yes? Everybody awake? Yeah? So the Manhattan distance from this one to this one would be 1, 2, 3, 4, 5, 6. And if you do 1, 2, 3, 4, 5, 6, it's exactly the same. Yeah, it doesn't matter. So let's take this heuristic. And given this problem, would you say it's admissible or is not? It is. It never overestimates, because you cannot find a way that is faster than, because you actually have to walk this way in this game, and you can only do worse than this heuristics. Yeah, because of the walls you will be worse. So how does hill climbing now work with what do we have to do for hill climbing in this algorithm, in this problem? So we start at 1A. We look at the two possible successes, and we look at the value according to our heuristics. So what is the value of 1B and 2B? 1, 2, 3, 4, 5 is the 1. 1, 2, 3, 4, 5. So it's the same. Okay, so that doesn't help us tie break. So we need to take randomly one of them. Let's take 1B. So we have 1C, 2B, and a 1 again. So then this one will be 6 again. This one will be 1, 2, 3, 4, 5, and this one will 1, 2, 3, 4. So I think this one is the best one. Yeah? And then this would give us the greedy algorithm. But we would always keep those one in memory. Yeah? So if we would use hill climbing, we would do exactly the same, but we would delete this one, and then we would delete those two. Yes? We would simply forget what we had written down there. Yeah? So that is hill climbing. And now comes the last one, and that is, or the last two, which are the same. Is this still readable at all? Okay, good. So now the last one is the A algorithm. So let's start with 1A again. And let's calculate the value. It is, so f of this state 1A is 0 plus, now we need the Manhattan distance, 1, 2, 3, 4, 5, 6. So this is 6. What are the children? We have again 1B and 2A. Both of them, so f of 1B is 1 because we have taken one step, and the Manhattan distance is 5, so this gives us a value of 6, and the other one I guess will do the same. So we don't have a very strong tiebreaker yet, so we just continue randomly, and this would be 1B, so we have 1C, 2B, and 1A. And you can see that here we have a 1, 2, so f of this 1A is 2 plus the 6 is 8, so this is really going the wrong direction. And those two will be probably again the same. But eventually this will give us one of the fastest paths that we can find. Yeah?
It would be smaller if there was more flat block boxes, right?
Yeah. So this is something that you have to be able to do in the exam, and that will give you easy points to score. If I give you one of those problems and you go through the whole machinery of algorithms, think about the difficult thing is my heuristics now admissible? And for the rest, just do the sum of this G plus the G, the total travel distance, plus the estimation of how long is it still the way, and then you're done. Have a good evening.
Okay, so the best first search algorithm is what we discussed earlier, no? And this time, again, as what we discussed about the A asterisk search algorithm. So first, we need to add a beginning node to the open list. Then repeat the following steps. In the open list, find the square with the lowest F cost, and then denote this the current square. Now we move to the closed square and consider H squares adjacent to the current square and ignore if it is on the closed list or if it is not workable. Do not do the following if it is workable. Check if it is in the open list. If not, add it. So you need to make current square as this square of a parent. You will now record a different cost of the square like the F, G, and H cost. So if it is on the open list, use G cost to measure the better path. Lower the G, the parent square. Now you need to calculate the other score, the G and the F scores of the square. If you find the path, you need to check the closed list and add the target square to it. There is no path if the open list is empty and you could not find the target square. Number 3, now you can save the path and work backwards starting from the target square, going the parent square from each square you go, till it takes you to the starting square. You found your path now. The task is to take the unit you see at the bottom of the diagram to the top of it. You can see that there is nothing to indicate that the object should not take the path denoted with the lines. So pathfinder algorithms like A asterisk help you plan things rather than waiting until you discover the problem. They act proactively rather than reacting to a situation. The disadvantage is that it is a bit slower than the other algorithms. So again, a asterisk algorithm works based on heuristic methods, and this helps achieve optimality. A asterisk is a different form of the best first algorithm. Optimality empowers an algorithm to find the best possible solutions to a problem. Such algorithms also offer completeness. If there is any solutions possible to an existing problem, the algorithm will definitely find it. So overestimation happens when the estimate of the heuristic is more than the actual cost of the final path. So this brings us to the end of the blog in discussions on the A asterisk algorithm in artificial intelligence. Thank you and good day, everyone.